Yeah, thanks for the introduction, and thanks for inviting me. It's a real honor and pleasure to be here. So I will talk about AlphaEarth Foundations, which is the work I've been doing recently, and then give you some hot takes, but not too hot. Let's get started. So as the introduction said, I'm Michael or Michal. I'm a research engineer at Google DeepMind. Um, and I think I don't have to convince anyone here that slides are very slow to update, that we've seen an explosion of Earth observation data in recent years. There is a bunch of different missions, Sentinel-2, Sentinel-1, and many, many others imaging the Earth with different temporal resolutions, different spatial coverages, different spatial resolutions, collecting petabytes of data, tens of millions of images across different bands of the spectrum, and the amount of data is only growing. And you would think that more measurement, very slow. More measurements should be a good thing, right? So we don't want to miss anything in space, time, or detection methods. So having more data should be strictly a good thing. So for example, if you want to respond to disasters or change, you need like rapid and accurate detection in time, and then reasonably frequent temporal refresh so that you can track the event of interest. Also, I'm sure many of you are painfully aware, clouds are a thing. They're unpredictable, and some places in the world are really, really cloudy. So you need a lot of repeated images of the same place to get like a cloud-free image or a good cloud-free composite. Also, higher spatial resolution can reveal stuff that you just cannot see otherwise, objects, even things like species. So that's also a good thing. And finally, we want to understand not just the surface of the Earth, but also the atmosphere, what's going on under the canopy, maybe even underground, maybe even oceans, right? So for that, we need to image across the entire electromagnetic spectrum. So having more measurements should help us with all of these problems. And yet, I will keep going until the slide updates. And yet, there are still significant barriers to using that data, both in terms of expertise and resources required. So this kind of graph here is a sketch. So as a practitioner, as a Earth observation data user, what you want is just the green dot, right? You want to get some insight, understand something about the world, make a map of something. But unfortunately, today, you still have to deal with the whole rest of the graph starting from the raw images, right? So there's a lot of non-trivial processing you have to do. I think you can get a PhD in just like one component of star pre-processing before you even get to feature extraction and modeling. Even if you use pre-processed data already, like the Sentinel collections and so on, you still need to worry about things like cloud masking, projections, aligning the data, and so on. All of which is quite non-trivial, especially if you're not a remote sensing or ML expert. And on top of that, even if you can do all of that, processing data at a global scale over multiple years can be very, very expensive. So one example here is this project that the European Commission did with actually the Google Earth Engine team on mapping global water change. So to that end, they processed like more than 3 million Landsat images, which took a week on like 10,000 CPUs. If you were going to do it on your laptop, it would take like 1,000 years or something ridiculous like that. So obviously, we cannot all be doing that, right? We can't expect practitioners to do that. So wouldn't it be nice if we could abstract away parts of that graph, or maybe hopefully the entire graph up to the green dot, so that practitioners who just want to make a map of water change or something don't have to worry about all that stuff that goes in beforehand. They can just do their modeling analysis and get the insights they want. So uh, one step we recently took towards that end is AlphaEarth Foundations, which is a model we launched earlier this year. So there's a blog post and a paper. You can read them if you're interested in details. I will give you a high-level overview and also how it fits into that problem and how it attempts to solve it. So at a very high level, you can think of AlphaEarth as this kind of virtual satellite. So what it does is it takes this source data, which is very diverse, the different satellites and even things like climate data and so on. It can be sparse in time, can be very non-uniformly sampled in time. It can have gaps in space, have different resolutions, correspond to different features of the environment and so on. So we take all that data and process it into this kind of nice, continuous, uniform record, which you can then query at any time and any place in the globe, and get like a nice, uniform, consistent representation of that place. We'll get to what that representation is in a second. But so the way we like to think about it is like it's a virtual satellite that you can kind of task to image any place over any time. Uh, so if it's like a satellite, like what does it measure, right? Well, what is its outputs? So this virtual satellite produces what we call embedding fields. So what is an embedding? If you don't know, it's basically like learned some n-dimensional vector. So in our case, it's just a list of 64 numbers that happen to lie on the n sphere, on the unit sphere. And that vector is like a very compressed and information-rich representation of that particular location and time period. So you can see an example of an embedding field here, sampled at 10-meter resolution. And once you produce such an embedding field, you can use it as you would some other data sources. Like, you could plug it in instead of Sentinel-2 composite or Landsat composite or whatever else you're using. But the nice thing is it now includes all of those other data sources, and it's already kind of nicely processed to be directly usable and kind of plug and play into your analysis workflow. So speaking of data sources, what goes into the model, we have a pretty diverse mix of input data sources. You will see it in a second on the slide. Once it updates, there's some usual suspects like Sentinel-2, Sentinel-1, Landsat. We also have climate data, topography, as well as some more exotic stuff like JEDI, and which is as you've heard from that talk earlier today, is the spaceborne LiDAR, and GRACE, which is gravitational measurements. That was actually pretty cool to process and use. So overall, we have 10 million like data cubes or videos, so series of images from a single location, which adds up to about 3 billion individual images. And the idea is we put in all of those sources so that you, as the end user, do not have to worry about, oh, which sources should I pick for my application, like which are important. We plug all of those in, we make the selection for you so that you don't have to worry about it. So once the slide shows up, you will see an example of an embedding field for the place where we are. So this is Copenhagen. You are more or less where the arrow is. And what I did here is I picked entirely randomly, so no cherry picking. I just picked 3 random channels from that embedding. And then for each pixel covering Copenhagen, I plotted those 3 channels as RGB. So obviously, in real-world applications, you would use the entire vector because you want all of the information. But even in this kind of simplified downsampled representation, you can already see a lot of structure. So for example, the dense urban core looks very different from the suburbs, which look different still from the kind of farmland and the green areas around the city. There you can see a lot of structure because there's different fields, trees, natural environments. And finally, the island to the east here, I think it's mostly like kind of tundra and foresty stuff. So you can see it stands out as kind of different still. So even in this very simplified representation, you can already see a lot of information density. So you can imagine that the full vector is very, very rich and very kind of information dense. And the nice thing is you can access it today. So we released the satellite embedding dataset. So it's a pre-computed collection of these embeddings for every year, starting from 2017 to 2024, 2025 coming soon, for the entire world at 10-meter resolution. You can access it on Google Earth Engine through this feature collection. Or if you're not an Earth Engine user, we also have GeoTIFFs in a GCS bucket, which you can just query and pull as you would any kind of cloud optimized GeoTIFFs. So now a little bit about performance. So as you can imagine, we tested the model on a wide set of tasks that we think represent the typical workflows people would like to use them for. We also tested it in like the low data regime. So if you have a data set with not that many labels, like how well does it perform? All of the numbers are in the paper, so I won't bore you with them. What I would like to highlight, though, is that raw performance is important, but equally important is sort of the qualitative aspect of using the data set. So for example, like an earlier version of the model, you could see these kind of swath artifacts coming from like how the sources were lined up. That is unacceptable, right? We don't want that, so we actually spend quite a bit of time eliminating all of those. You also get gaps in the data. I think Sentinel-1 is the worst offender here. So funnily enough, the model actually knows how to deal with missing input sources. That was actually a bug in the inference pipeline, but still something you have to deal with. It's not acceptable, so we had to solve it. And finally, a slightly subtler point. So if you look at Google Earth or Google Maps, like the base map sometimes has these kind of weird artifacts because it stitches different images together from different sources or different times. Now, if you're just looking at a base map to, find your favorite restaurant or something, that maybe is acceptable. But if you're trying to get kind of precise quantitative measurements or predictions, that is absolutely not acceptable. So you need to ensure that the embeddings are very consistent across time and space so that you can do meaningful comparisons and make sure that your map generalizes to, arbitrary time and space periods. So we spend a lot of time actually doing that. So what can you do with the embeddings? Pretty much you would expect. So starting with a simple similarity search, where you take an embedding for a particular location, and then you compute some kind of a similarity measure with every other point in the world, and you see, what lights up, what's more similar, and you can do like retrieval or just kind of visualize it in this kind of nice plot. We have a demo app that you can play around with. You can do classification. So for example, crop type is one example. You can also do regression, like above ground biomass, evapotranspiration, any kind of biophysical variables or other stuff you're interested in. We actually have evaluations for both of these. And finally, my favorite application is change detection. So because the embeddings are fairly consistent in space and time, you can take the dot product between embeddings from the same location across different years. And basically how similar the embeddings are tells you how much this place has changed. So the example here is forest clearing. So kind of brighter colors mean more dissimilarity. And you can see that even from this kind of very simple unsupervised method, you actually can get pretty meaningful change detection and then kind of follow up and see what actually changed there. So that's a pretty cool application. So, okay, that's what you can use it for. Are people actually using it? And the answer is yes. We had quite a lot of, we both a very exciting trusted tester program before the launch, as well as many very cool applications after the launch. One I would like to highlight is the US Department of Agriculture recently released their cropland data layer, so the crop map for Hawaii for 2025. And this was actually the first time they were able to do it at a 10-meter resolution and at a higher class resolution. So they're able to capture locally important crops like taro, sweet potatoes, bananas that maybe don't grow as much anywhere else in the US. So you don't have as much data, but are very important for the local Hawaiian communities. So it was kind of a nice show that, it's global, but you can also use it for very important local applications and get really, really good results. Okay, that was AlphaEarth. So honestly, you can read about all of that in the paper. So I thought like, well, what would be interesting to talk about? So now we'll get my hot takes on foundation models. I hope they won't be too hot, but let's go. So yes, foundation models. We had a panel discussion today that was very interesting and touched on some of the points I'm going to discuss now. So I would argue, and I think hearing from the panel discussion here and the comments from the audience, it's not very controversial that EO foundation models have not yet led to some sort of a renaissance or breakthrough in mapping and monitoring. By the way, I'm focusing here on mapping specifically because that's what I'm interested in. Mapping broadly understood as there's some quantity or property I want to measure over the whole Earth or like some particular region over time. So we haven't had our AlphaFold moment yet, and it's not for a lack of trying. There's a lot of really exciting papers at this workshop, at main the NeurIPS main NeurIPS track. Every day it seems like we get like a new, really, really good high performance foundation model with great research ideas, and yet we haven't yet had this moment like AlphaFold did, where there was like a step change. If you don't remember AlphaFold, it was basically a model for protein folding. And the best protein folding model for time was kind of sort of consistent, hovering about 40% accuracy. And then AlphaFold came and suddenly unlocked things. It was a step change, unlocked things people could not do before because the models were simply not good enough to be useful for anything, right? So imagine this kind of power, but for Earth observation. Imagine what could be our AlphaFold moment. And I don't think we've had it yet. Another example is language models. So ChatGPT is a thing, Gemini is a thing. And if you ask someone 10 years ago, like, can an AI model write an essay or like a poem or write code? People would say like no, and that's like science fiction. That's like many, many years away. And yet today we kind of take it for granted that, yeah, obviously you just ask an LLM and writes an essay. So language models have shown competencies that just did not exist before and people did not even imagine could exist. Like they were like, oh, that's not something you can ask a computer to do, right? And yet now we can do that. So imagine what could that be but for Earth observation, right? What would be our moment where we show something that there's simply not something that could be done before? So why is that? Why we haven't had that moment yet? I think there are many reasons. I obviously don't know the answer, but I think part of the answer is that there is currently pretty high overlap between the developers of foundation models and the users of foundation models. So different labs build different foundation models, and then kind of the same mix of people uses them to, benchmark, maybe solve some problems if it's also like an applied lab, but it's more or less the same community. Uh, However, the community of actual EO practitioners, people who extract insights from Earth observation data, is much, much bigger. And we're not really eating into that circle fully. And those people tend to be of a very different profile than us ML experts. Uh, they have their own workflows. Very often they use like QGIS or something, Earth Engine, like an Earth 10,000 line Earth Engine script. They have no idea what Hugging Face is or how to run PyTorch or what a GPU is. And even if they do, they very often don't have the resources to do it. So foundation models are easy to build for ML experts, but I think are still fairly challenging to utilize by kind of the broader community who are not necessarily ML experts. So for example, if you do fine tuning, if your model needs fine tuning, that typically requires more data than people's existing workflows that use, I don't know, composites or CCDC. And furthermore, requires some extra expertise, like you need to understand how to pull the model weights, load them into memory, how to use PyTorch, work with GPUs, and so on. Many people working on important stuff in policy, ecosystems, and so on simply do not have this kind of expertise. Even if they do have that expertise, compared to existing methods that rely on composites, CCDC, whatever, EO foundation models are much more expensive to run and very often require specialized compute access. There is a push towards smaller and cheaper models, but then again, there is a trade-off with performance, and if a model is cheap to run but not as good as a composite, then what's the added value? Also format, also like data, EO data is very different from natural images. For example, in a natural image, like if you're off by 1 pixel, that probably doesn't change anything. If you're running a foundation model that produces, let's say, 60-meter patch embeddings, and you picked your projection wrong in your data pipeline as a user, and you're off by 1 pixel, then you're off by 60 meters on the ground, which, depending on the application, that could actually be pretty meaningful. And these types of issues are very hard to spot. And if everyone is kind of doing them all over again, this creates opportunities for costly mistakes like that. So I think the conclusion here is that foundation models specifically have not yet enabled our community to do something that they couldn't do already, and especially the kind of broader EO practitioner community. So now embeddings. Now I worked on AlphaEarth. I told you about the embedding dataset, so you must surely think that I think embeddings are the solution. And I would say not really. Embeddings are definitely part of the solution. I think whatever we see in the future will involve embeddings in some way because they have this nice property of summarizing lots of data into this compact, fixed, uniform representation that then you can kind of cheaply reuse without having to rerun the model. So there is definitely a role for embeddings, and they are a very powerful tool. I think it's still very early on, so there's still a lot to explore, a lot to learn, lots of different embedding approaches and models and ways of using them to try. But as of today, embeddings are not the right fit for every single task. So for example, I talked to some people around here, and very many of you come to me with interesting use cases like, oh, can you do the North Pole? Or like, can you do the ocean? I'm like, not really, because there are trade-offs in if you want to go broad spatially and temporally, you're trading off for some other things. And in particular, there's this, I think, 3 axes here, generality. So like what can you do with your embedding? performance, how good it is at any particular task, and compactness, like how small it is, and therefore how easily you can pre-compute it for the whole world. And you can really kind of pick two. There isn't really a solution yet that kind of aims picks like, slots in right through all of them. And I don't think it's really possible. Like in AlphaEarth, we try to balance all of them to give you, something that uh, you can run for the whole world at a reasonably high resolution, and that's reasonably good performance. But again, that's trading off, like, for example, if you're doing something very high resolution, like detecting individual trees, maybe a 10-meter embedding is not the best fit for you, right? We could make the embeddings higher resolution, but then we're trading off with, we would have to make them even more compact so that we can actually compute them for the whole world and so on. So there are trade-offs, and I think there is no like single embedding method that can meet all of them. So more of it once the slide updates. I think embeddings are nice because they're easy to utilize and their potential is not really very well understood yet. So we also, for example, need to think more about things like how to adapt to like real time. If there's a natural disaster, right, and you need some kind of a insight or signal now, like how do we let you run the embedding model to get kind of embeddings for this kind of snapshot of time that you're interested in? And we actually have some thoughts on that. Maybe some exciting announcements coming up soon, but I cannot tell too much yet. Also fixed resolution, that makes it very hard to have like one scale fits all. So 10 meters is a good trade-off between kind of what you can see in the image and how compact it is. But there are use cases, like I said, where you simply cannot, 10 meters is simply not good enough. So to put a more positive spin on it, I think there's a lot of opportunities for a diversity in different approaches that could all have a role to play. So you could have maybe more general global scale embeddings at 10 meters like AlphaEarth, and then you could have a more specialized model that produces high resolution embeddings, maybe like even from aerial imagery, if you really care about very fine-grained details. Some more like task-specific embeddings. So if you care about the oceans, maybe a generic embedding is not good for you, but there is a model specifically for oceans that uses the data available there, and so on. And that also creates opportunities to coordinate on APIs and frameworks and specs to make sure that these embeddings are easy to kind of use and reuse and mix and match. So maybe you get some information from the generic 10-meter embedding, but you also have like a high resolution embedding that you append to it. And that gives you you can do that easily, kind of mix and match as you can sources in Earth Engine. And that gives you a much better model overall than if you just used a single model or a single embedding. So the short answer is I don't know what the answer is. I don't think anybody does. I think there's still a lot of very cool research to be done. So I will leave you with, let's say, some principles that guide me and our team in what we're doing. So coming back to the beginning of my talk, I think more measurements should be a good thing. And that's something we should strive to make as feasible as possible. Make the wealth and diversity of Earth observation data as easy to use and accessible to people who can actually make an impact in the world using it, but might not be remote sensing or ML experts. Those people, the users, like sure, they care about performance, but they also care about other things, right? Ease and cost of use. They care about compatibility with their existing workflows. Like we had one trusted tester who they were actually pretty competent in ML and so on, but they were constrained because they were working for the government, for the US government, and they could only run their analysis on this like ancient Pentium machine that was certified to have the confidential data they were using. So there's stuff like that they couldn't run a big foundation model on GPU if they wanted to. Spatial and temporal consistency, so that your analyses are can be carried forward in time, backwards in time, across the globe. All of those things may be a bit boring compared to cool architectural innovations and great benchmark performance, but they actually do matter for the users, and I think it's important that we think about these things too. And ultimately, enabling users to make better maps faster is the core problem for me. I don't really care how we get there as long as we can give people value. That's it. Thank you.